Today I will talk about an incremental learner for language-based anomaly detection in XML. So you have heard already that XML has some pretty nasty screw-ups. To make it short, it's a text-based data serialization format, and it's used in many communication protocols that you already find in cloud computing. It's text-based, so they like it for the heterogeneous environments. So SOAP is a classic protocol for web services. XMPP is in the new standard for intercloud messaging. SAML is a protocol for single sign-on. XHTML is the XML variant of HTML, and so on. So you find XML basically everywhere. And in the LangSec sense, you can think about schema validation as a first-line defense. A schema is like a tree grammar. It specifies types of elements and production rules, how these types are allowed to expand in a document. And validation is then to check whether a document conforms to a schema, and it should reject unacceptable inputs. But it's not that easy because there are two language theoretic flaws. First, the industry standard XML schema has so-called extension points for achieving composability, and the extension points are basically wildcards. Second, we have references in XML. So ID-based references are self-references in a document, and they raise the expressiveness beyond context-free, which makes it very hard to validate. So how can I spot an extension point? This is a fragment taken directly from the SOAP specification. It specifies the type for header. The SOAP protocol specifies a message format. The envelope has a header and a body. And in the header, it just specifies any element can appear. And the namespace just has to be different from the SOAP namespace. And the last argument, process content lags, this makes it really bad. Process content lags tells the parser, when you validate such a document, try to find a schema for this element at this place. If there is no schema in the scope of the parser, just skip validation. So what can you place there now? So you can easily make some denial of service attacks, like many nested elements, many elements in general, but you can also place more involved attacks. So the signature wrapping attack combines this problem of extension points and ID-based references. XML digital signatures are used in many protocols like WS security for SOAP or in SAML single sign-on to digitally sign a part of the document and store the signature at some other place. So the group of Somorowski have looked at SAML implementations, and they found in 2012 that most of them were vulnerable to this kind of attack. And to make it more understandable, I have a small example on the slide. This is the information set of a SOAP message. It has an envelope and a header. And in WS security, the signature resides in the header, and the signed part is the body, and the reference of the signature points to the body. And when this file is consumed by a service or by a client, it goes typically through a processing pipeline. They first check whether the signatures are all valid. It's a Boolean decision. If yes, then process the part. So the problem arises when the digitally signed part is not necessarily the process part. Because there are extension points, an attacker can move the original content into some random wrapper in the header and place its own instructions there. And the business logic selects the body for the instructions, and the signature is still valid. So this is actually an example from 2009 for Amazon EC2. Using this attack, it was able to create arbitrary SSH keys for other hosts in the cloud. And the attacker only needs a signed message, the one to the left. And in this attack, it was easily possible. Back then, it was possible to get them from network sniffing, or users even posted them on the Amazon support forums for debugging purposes. So once the attacker got the valid message, valid signature, he could utilize it. So how can we encounter this attack? There have been several attempts to close this loophole. in my opinion, the one that makes most sense is the one by the group of Jensen. It's just removing the extension points. But this turns out to be hard. The extension points are in basically all the composable protocols I listed before. So we have a combinatorial problem if we want to create a unified schema. So if I have 10 schemas with 10 extension points, I can combine them arbitrarily, and the result grows exponentially. So removing them is hard, and this motivates my research, which I call language-based anomaly detection. The idea is to learn the acceptable language at the particular interface of an XML-based system. What do we need for this? First, we need some representation of the language. I chose an automaton-based representation. I call it data type XML visibly pushdown automata, very long name. The idea is it accepts mixed content XML in a streaming scenario. Why mixed content? Because we have it in the HTML scenario. Why streaming? The XMPP protocol is an XML stream protocol. So this is the most generalized form of language representation. In XML, we can have character data, and the automaton generalizes data using data types. And from this automaton, another form can be created. It's called character data, XVPA. It's basically the same. It just has some optimization for stream validation, so it can check in linear time. Second, we need some learning algorithm. And I specify an incremental learner using the ideas from grammatical inference. The learner constructs such an automaton from examples, and it also provides 2 operations for unlearning and sanitization of the automaton, so we can handle poisoning attacks during the learning process. And third, learning is, of course, some form of induction. It can never be completely valid. It can only be very strong. So we need experiments, how it works in practice. And I have a train and test approach, and in total 4 data sets. 2 of them were generated using a stochastic XML generator, just to do the tests, and 2 more advanced scenarios using the Apache Axis 2 web service. I implemented my own web service, like the tutorials tell me to implement. It was, of course, vulnerable against all the attacks. And I used tool support and manual attacks to make some examples for testing. So how does an automaton look like in this class? Of course, it has states and transitions. What makes it very special? It has a alphabet. It has actually 3 alphabets: a call, return, and an internal alphabet. The call alphabet is for the start element events, the open tags in the document. The return alphabet is for the end element events, for the close tags. And the internal alphabet is for data types, so something that happens between an open and a close tag. Of course, this is a pushdown automaton, so of course it needs a stack, and it utilizes the states for the stack alphabet. The names of these alphabets might indicate where the automata class originates from. It's from program analysis, where call and return were used to model function calls and returns, and the internal alphabet is used to model what happens in a function. So the states are then partitioned into so-called modules, shown as boxes. The modules have an entry state and exit states, and the module is exactly a schema type, what you have in a grammar. We have then transitions within modules and between modules. Transitions between modules are for open and close tag events, and they push and pop the stack. Transitions within a module leave the stack unchanged. So this gives the automata very nice decidability properties. And the CXVPA is a special form. It just optimizes how internal checks are done in linear time. This is now the incremental learning step. There are several algorithms involved. There is a learner component and a validator component. The learner computes an updated automata, and the validator validator uses the fast representation for checking. And the learner receives a data typed event stream. This means this is an event stream where the character data is already replaced by minimally required data types to model these texts. There are two internal representations, the A and the omega. The A is an incrementally updatable pushdown automaton, and the omega are frequencies of states and transitions learned from data. So they are like weights for the edges and the states. And the inc-weighted algorithm updates these internal representations. Trim removes the zero-weighted states and transitions. GAN XVPA generates the modules and does some minimization. And then a learning step, an incremental learning step is done. So to give you an idea how incremental learning works, the fundamental idea is that every event stream prefix of a training document gets a unique state. And we do this by naming the states using U and Y, U and V. U is a typing context, and V are the left siblings. And we then merge two states if they are locally the same. And the locality is specified by two parameters, K and L. So let's look at this example. This is a XML info set. It is a document where a dealer has used cars, new cars, and advertisements for them. What makes this example interesting is that the advertisements for used cars are a different type than the advertisements for a new car, because a new car does not need a year, because it's new. And the learner should, of course, be able to distinguish these cases. So the red part and the blue part together are all the typing information a deterministic parser needs to decide the type of the add element, of the rightmost add element. We use the typing context and the siblings to derive a unique state. And from this unique state, we can create a localized state. And this is the whole magic of the learning. The question is it sound? Yes, in many cases, because there were studies on complexities of schemas in practice. People tend to use very simple production rules where locality works, and people also tend to use very limited typing contexts, local typing contexts. So I can usually find small parameters K and L to do a very good generalization. So what about poisoning attacks? I mentioned we have these omegas, the counters of frequencies, how often states and transitions have been learned. Unlearning is for the case where I discover, oh my God, I have learned an attack unintentionally. Then I can remove this attack by simulating this corresponding attack and decrementing the edges. And the trim function then drops these edges if they turn to 0. And sanitization is for the case where I have hidden poisoning attacks in my model. The assumption is there are only few of those. It's a statistical assumption. And I can get rid of them if I decrement all the counters by 1 or by 2. And all the edges that drop below 0 are then removed. So the low frequent events. So as I mentioned, I tested it in total 4 scenarios. For the attacks, I used both manual skills and also tool support. And for evaluating, I measured the learning progress. I have a train set and a test set. I randomly pick a training example, do the incremental learning step, evaluate the whole test set, measure the binary classification performance, and I also count the mind changes. The mind changes are the number of states and transitions that have been added from an incremental learning step. So if the model is complete, there are 0 mind changes when learning. And if it learns a lot, there are, of course, many mind changes. And these mind changes, they are useful heuristic in practice to see if my model has already converged. So, but still as a heuristic. These are 2 examples. The lower axis are the training iterations. And the dots represent the mind changes. In the first training step, there are, of course, many mind changes because many new states and transitions are allocated, and they get less and less. The error bars in the above graph, they correspond to the randomness, because I randomly choose an example. So I did these runs several times and measured the best and the worst performance. This is why I have error bars in the graphs. And in all cases, there were only few examples necessary to converge to a stable representation. The F1 score is the overall classification performance. F1, 100% means that it did everything right. In the catalog dataset, it was about 91%. And in the other dataset, the Woolen-Shop out order, this is the Axis2 example, where I used the signature wrapping attack, or many signature wrapping attacks, many different combinations of them. And in this dataset, usually after 2 or 3 examples, the learner had already a representation that was good enough to identify 100% of the attacks. This was because the Apache Axis2 is a plugin where I, for my Java development, where I write Java beans and it generates all the XML magic behind automatically. And because of this automatic generation, the grammar structures are very restricted. So the learning can be done very quickly. So to sum up, in all the experiments, the learned representation outperformed the traditional schema validation approach. All signature wrapping attacks were detected using this method. The classic schema validation detects none of them because of the extension points. There were also no false positives. However, there were some false negatives. They were related to the data types, the data type abstraction of content. And if a data type gets too general, it might accept an attack there. And there was also very fast convergence in all the experiments. This was basically a rough overview what I did. In the paper, there is, of course, more. There are the specifications for the automata models. There is also the lexical data type system for inferring data types from text used for the data typed event stream. And there are also the specifications for the algorithms for the incremental learner, and also more details on the experiments, how I put them together. So what are the use cases of this? Of course, a security mechanism for XML-based interaction, especially when systems use composed schemas. One example that is currently in development is an XML-based firewall for web services. But I think this method could have more applications. So thank you so much. I'm ready for questions.